Hello everyone. So today in this video we can discuss the first four problems from the latest AtCoder beginner contest 240. So let's start. The first two problems are not too difficult, but yet we're gonna do them in a very simple manner. The first problem is a new generation ABC. So you're just given that this is the 214th AtCoder beginner contest. So the AtCoder beginner contest, from the first AtCoder beginner contest to the 125th, there are four problems each in each contest. Then further on from 126 to 211 there are 6 problems, and from 212 to 214 there are 8 problems. Now you are given n between these number of contests, and you just have to tell that in that contest how many problems are there. You just have to write down if and else condition. If n is between 1 and 125, then the number of contests is 4 and so on. So that's the logic for this problem. It's not too difficult. You just have to write down 3 if else conditions. The next B problem is how many triplets of non-negative integers a, b, c satisfy the following condition, which is a plus b plus c is less than equal to s, as well as a into b into c is less than equal to t. Now this problem you can easily understand from the constraints and from the equations which is given to you. Now what you can see here is that s is up to 100. Now s is up to 100. What you can easily understand from this part is, let's assume I have a plus b plus c less than equal to 100. Now the maximum value of a can get up to 100 and the minimum can get up to 0. Why? Because see, if individually a is equal to 101 and b and c are also greater than equal to 0, then this will increase. But it is always given that the s value is always less than equal to 100, and thus ABC individual value will always be less than equal to 100, and the maximum value of A can get is up to 100. As you can see, same we can apply for B and same we can apply for C. So it means that the maximum value for ABC from this equation is 100. If you take the next equation, which is A into B into C less than equal to T, now T is little bit greater, which is, as you can see, up to like 10,000. Now if you take the same logic here, let's assume that in this same logic, if I assume that b and c are the smallest, if b and c are the smallest, which is equal to 1, then what is the value of a if t equal to 10,000? If t equal to 10,000, then the value of a will be 10,000, because LHS equal to RHS, and thus the maximum value of a from this equation can get up to 10,000. So the minimum a from this equation is up to 100 and a in this equation is 10,000. So the maximum is 100 only, or actually the minimum of both of these values is 100, and thus we can easily assume that the value of ABC will be up to 100. And thus if ABC is up to 100, we can just use an O of n cube approach, which can easily pass the time limit, and thus we can just write down 3 nested for loop, and check for every value of a, b and c from 0 till 100. Okay, just check like a equal to 0, b equal to 0, c equal to 0, then a equal to 0, b equal to 0, c equal to 1, and so for all the values of for a, b and c from equal to 0 till 100. And that's the logic for the second problem, and just check that what's the value of a, b, c which satisfy both of these conditions. Okay, I can also show you the code part. The code is also not difficult. You can see the code here also. I will link down all the codes in the description, so if you want the code, you can check that code out also. So I just have written that the nested for loops, 3 nested for loops, if both of the conditions are satisfied, then the answer is you just increment the total value. Okay, next move down to the C problem. The C problem states that there are n creatures standing in a circle, now called snooks 1 till n. So there are n snooks which are standing in a circle. Now when snook I receives a gem at time t, so the snook will receive a gem at time t. If at any time snook receives a gem SI unit of time later, he will give that gem to I plus 1 snook. So if he has the gem, he will like observe that gem, let's assume, for SI minutes, SI of time, and then he will pass on to the AI plus 1 snook. So it is like in a circle, and thus the next snook will pass on to the next snook. Also additionally, Takahashi will hand a gem to snook I at TI time. So you are given that one snook can get a stone by the adjacent snook, so the snook, like before, it can give the stone to the other snook as well, and also Takahashi can give the stone to any particular snook at a particular TI time. So you have to just tell what is the first time a snook will held the stone in his hand. So as you can see, maybe he will get the stone from Takahashi, or the other case can be the snook can get the stone from the next snook which will give the stone. So you just have to find out the minimum time it will take to for one snook to like choose the gem. Now if I take down to the drawing board to even make it more clear, you are given that there are some snooks. So it's like a circle. It's better to draw it like a circle. Okay, now it is already given that this snook will get time like a gem at time t1. This will get a time t2, t3, t4, t5 and t6. So at this time they will definitely get a stone, but maybe this snook will get the stone the first time at maybe 0th second. At the 0th second this snook will get the stone. Now after, let's assume it is also given some SI time. So SI1, so S2, S3, S4, S5 and S6. Now after S1 minutes this snook will transfer the gem to here, but maybe, so how much time it will take for this to transfer to this? Ti plus S1 time. So it will receive a Ti, and this, so how much after time this snook will get the stone? Ti plus S1 time, T1 plus S1. But also it can happen that T2 at which Takahashi will give the stone earlier. So you just have to find out that because the stone move in this direction only, there are two options. Whether he can get the snook will get the stone from Takahashi, which is like T time, or he will get the stone from the upcoming snooks besides snooks. So the time at which he will get this like stone here is like, for a particular snook you will just have to find out the minimum of the time at which the snook will get the stone, which is like Ti, and the time at which that particular snook will get the snook, which is the previous snook. So if I want to find out for this snook, this is like Si. If this is like Si snook, I want to find out how much time it will get. So you just have to find out the minimum of the time at which that particular snook will get the stone, which is Ti. So at Ti it will definitely get a stone, or else what is the time at which this particular previous snook get the stone? So previous snook get the stone at maybe I just store some answer variable, and this previous snook will get the answer of snook of Si minus 1. The snook S minus 1 at which point it will get, and after that that particular snook will take Si time to send that stone to the next snook. So that's the time the next snook will get the stone. Now how will get the time for the previous snook? So what you can easily understand here is that the first snook will get, so you have the minimum time, you have the time at which Takahashi will give a stone to particular snook. So this snook will get the stone at Ti, like T1, T2 and so on. So what you can see here is, sorry, just remove out this out. Yeah, so you just find out the minimum of all the T's. So find out the minimum of all Ti. This will give you the minimum amount at which at least one snook will get a stone. So maybe minimum Ti is 2 seconds. So after 2 seconds, one snook will get a stone. Now after one snook will get a stone, I know one time. Now from that snook, I will start doing my counterclockwise direction move. So I will move from that particular snook in the counterclockwise direction and find out the time it will take for the next snook to get the stone. So if this is the first snook which will get the stone, I will find out the Ti, minimum Ti of all of them, and then maybe this is the minimum Ti, the minimum time at which the first snook will get a stone. So this is the minimum Ti. From this stone will be carried forward to this snook after S1 seconds. So what will I do? I will find out the time it will take for this snook to transfer the stone, and also the time at which this snook will already get a stone will T2. So find out the minimum of them. Now you get the time at which this snook to get a stone, then do it for this snook and so on. So I hope you get some type of intuition how we'll solve this problem out, and that's the whole logic for this problem. I'll take it on to the code part now to make it more clear. So let's move on to the third solution. The solution is what you are actually doing here is that you are first storing out Si and Ti, which is the time at which it will observe and the time Takahashi will get the stone. Then we'll find out the minimum time among all the particular time, because at that time at least one snook will get the stone. and we'll find out the minimum index from which we have to start. Then this is the answer variable at which I'll store all the answers. Okay, and then which I've told you, the first nuke will get the stone immediately because that's the minimum time the first nuke will get a stone. So I will store out the answer because I know that for the minimum nuke, that's the time, particularly that's the time he will get the stone. So I will store that answer for the minimum nuke only. Then I will iterate over from that particular nuke the next nuke. So I will go to the current nuke I am on is the ith nuke I am on. But because it is in a circle, what we can do here is we'll mod it with n. So because we have n snooks, so we'll just do n for loop from 0 till n. But because if we go outer bound, the best way is to round it out. So if we go outer bound till n, just come down to 0. That how we can do that in a cyclic manner, we just mod it with n. So my current index I am on is I plus index, and the next is obviously just add 1 to it, and obviously just mod with n. Then for the next answer is the minimum of the next time, because the next time the snook will give the stone, or current answer plus the time it will take for the current snook to pass to the next snook. You just have to find out the minimum of both of these possibilities, and that's the answer. Just print out all the snooks in this particular manner. So that's the logic for the third problem. Let's move on to the fourth problem now. The fourth problem is sum of maximum weights. The problem is telling you that you have a tree of n vertices, 1 till n, and every edge is having some sort of a weight wi associated to it. So first thing which comes to my mind is maybe I have to use some Dijkstra, but always try to first read the problem out and then come to some conclusions. The problem is telling you that for different vertices u and v, f u v be the greatest weight of all, like of an edge containing in the shortest path from the vertex u to v. So it actually means in simple terms here is that f u v is a function, which means that if you find out the shortest path from u vertex to v vertex, you have some edges, like you have to iterate over some edges, then those edges will have some weight, and the maximum weight among all of those edges is the f of uv. Then you have to find out actually the summation of all of the possible pairs of f of uv's. So if there is a tree, so let's try to draw it out to even make it more clear. So maybe there's a tree like this. There's a tree like this, and then like maybe there are different pairs, so I want to go from this to this, there's one pair, or I can go from this to this. So there's always a shortest path in the tree. There's only one single path which is the shortest path in a tree. Okay, so as you can see, maybe if I want to go from this node to this node, I will take this path. Okay, so I will just remove out this type. So if I want to go from this to this, I will take out this path which is the shortest path. Okay, and maybe if I want to go from this to this, I will take out this as the shortest path. So that's the, like, there's always only one shortest path. Now for the shortest path, as you can observe, there are some weights written on each edge. Maybe this is 5, this is 3, this is 7, this is 3, which is 8, which is 9. Now if you want to go from this to this, the maximum among all the edges is 5. If I want to go from this to this, the maximum among all those edges is 8. If I want to go from this to this, the maximum among all of them is 9. So I hope you're getting the intuition. Now for every possible pair of nodes, you have to find out the summation, what is the maximum of f of u. Now in such type of problems, it is clear that you don't have to use Dijkstra here. But what you can easily observe here is that instead of finding out of every pair, like every pair of vertex, in such type of problem, because the number of pairs is very large, but the number of edges is small. So we have to try and think over every edge. We just have to find out that in how many paths actually, because see, if there are n vertex, and for every vertex there are n minus 1 edges, so it will go, and n is up to 10 to the 5. So this will go very large. You cannot iterate over every possible pair and then for every possible pair find out the maximum edge and then add it out. It will become very large. But instead what you can see here is that the number of edges is small, which is n. So iterate over every possible edge, and you have to find out that in how many paths a particular edge is the particular answer. What I mean by this is, maybe there's one path like this, one path like this. So maybe if I'm talking about this particular edge, in how many paths this edge comes across. As you can see, this edge comes across in this. If I want to go from this node to this node, this edge will come. If I want to go from this node to this node, this edge will come. If I want to go from this node to this node, this edge will come. So at different nodes pair in which this particular edge will come. And in all of those paths, I just want to know in how many paths this is the node or this is the edge, which is the maximum edge. Now, how we can find out that? That's the main problem. So now what you can simply observe here is that instead of, because see, if we go from the smallest edge maybe it's 1, 2, 3 and 4 and 4 and 5. Now what you can see here is, if I'm just talking about this section, only these two nodes, for these two nodes only 1 is the answer. If I just extend this logic and take this also node into consideration, I want to go from this to this, then 4 will come to play and that's the maximum. And thus this is in the longer way. If I want to just take out this path, from this to this the answer is 1, but I want to go from this to this, then the answer will become 2. So as you can see, as the weight increases out, then the path I'm taking out will change. The maximum value I'm talking about is changed. So it means that I just have to find out that in which edge, like how many nodes are there, which will actually form the, like for that node particularly, we'll have to talk about and find out that for a particular edge, like for this edge, how many nodes are there which are actually helpful in taking that edge as the maximum weighted edge. So what you can simply do here is that I'll talk about here, just like sort out all the edges, like take out all the weights. So take out all the weights from all the edges. So let's assume that the weights are 1, 2, 3, 4, 5 and 5. Just take out all the edges, like all the weights, 1, 2, 3, 4, 5 and 5. I've taken out all the particular, as you can see, like weights. And what you can do here is, we are actually using DSU, which is like this disjoint set union, in solving out this problem. What we can simply do here is, I'll just show you out. Disjoint set union means that there are different nodes and there are no edges. So I'm just drawing out the same tree without the edges, as you can see. Now we'll just iterate over the particular nodes from left to right, actually these weights from left to right, and take out the smallest weight. This is the smallest weight, and we know that this one weight is joined by these two nodes, so just join them. If I join them, then easily I can know that only number of nodes which are connected by this node, like when I join this, there are two sections or like two groups. This is one group and this is one group. The groups which are formed by joining this edge is only the one which is helpful, that will have this particular edge as the maximum one. I hope you're getting my point. So as you can see, let's assume now there are two. So now 2, if I join this is the edge which is having 2 as the maximum. If I want to join this, now as you can see, the group change. One group is this. So if I'm talking about this edge, this is one group and this is one group. What I'm talking about group is the nodes which are on the, like as you can see, the number of groups, like this is the connected nodes on one side of this edge and the number of connected nodes on one side of this edge. So as you can see, this is one connected group and this is one connected group. So as you can see, the group here is 2 of size 2 and the group of size here is 1. So as you can see, for this, if I want to find out how many pairs are there which are having 2 as the edge, which is the maximum among their pair, for all of these nodes in the one particular group, if I want to go to the next group, so if there are n nodes in one group, n1 nodes in one group and n2 nodes in another group, then the number of pairs I can form for which 2 is the maximum node is n1 into n2. Why? Because for every n1 node I can go to n2 node, and that will have, with like for that node I have to go through this edge, and that's the maximum, as you can see. And thus what you can simply hear is that, and for this node, what is the maximum node value, which is 2, because I have to find out f of uv, which means that how many roots are there which is having that is the maximum value. So there are n1 into n1 roots, and for those roots 2 is the maximum value. So I'm actually finding out all the roots for which 2 is the maximum value. So now I'm talking about 3. So 3 is actually joined by this. So I joined this edge. Now what is the group? As you can see, this is one group. Now this will form one group and this will form one group. So like this is n1, this is n2, and this is like, again we just add n1 into n2 into like 3. and we just keep on adding this. So we are keep on adding one edge to this whole graph and finding out the size of one group and another group. We just have to do this using DSU. So it's just we have to first find out the size of the first group and the second group. There are like functions in DSU, disjoint, set, union, to find out the size of one group and another group. And there's also a function to merge out two particular groups, because I'm actually connecting these two groups, so we have to just merge them out. So that's the logic for this problem. Just have to implement a very simple DSU. If you know some knowledge, or you can watch out my previous DSU video to understand more on this logic. I will link down that video in the description. So we'll go to that logic part. We have gone through the logic part. Let's move on to the solution part now. So what you can simply see here is that for DSU codes, we have to write down 2-3 functions. We have to first write down a standard global array for parent and for size. Parent is what is the parent for every group, and size is what is the size of group in which we are for any particular node. So maybe if I'm on node 5, what is the size of the group in which 5 is there? So if there are different groups, as you can see, there are different groups. There's like group 1 and 3. So as you can see, if I want to find out what's the group size of a group of a node on which 2 is there. So if 2 is there in this particular group, what's the size of this particular group? So we can find out that also. So what there is so that's the first function to find out the parent of any particular group, because you only talk about the parent. So this is a recursive function, and this is the merging function to merge out two particular groups. So this is the solve function, in which we'll first initialize the parent is equal to I. So every node is a self parent to itself, and the size of every group is 1. It's just a standard DSU code, in which we have to first take the input of U, V and W, because we have to sort according to W, which is the weight. So we have to take weight as the first value in this whole vector. Okay, then we sort out, because we have to sort according to the minimum to the maximum. We have to first join out the minimum edges, and then we'll move to the maximum size edges. Then what we'll do, for every particular edge, what we'll do, we'll first find out their parents, and for finding out their parents, we can know the size of that particular group which we want to join. Now for adding the answer is multiplication of the weight into the group 1 size into group 2 size, what I've already done in the